In the previous module, we have introduced two basic functions. The first one that we have seen was called as an impulse function, and the second one we saw as the unit step function. We have introduced both of these unit impulse and unit step in continuous time and discrete time case. We have seen that any signal can be represented with the help of impulses. Similarly, we can represent what are called as piecewise linear functions with the help of unit step signals. Now, what do you mean by these piecewise linear functions? These are the signals which are linear in fragments. For example, let's take an example. So, for example, if we have signal something like this, example, see we have signal that is 1, from say 0 to 1. So let this be 0, 1 with an amplitude of 1, and let this be x of t with a function of t. Now this is an example of what is called as a piecewise linear signal or function. As we can see, this signal is unity or it's constant between 0 to 1. So it is a kind of linear. In fact, it's a constant from 0 to 1. Another example that we can have here is something like this. So another example, it would be, let's say the signal is like this. Let this be from 0 to 1 again. Let this be 1. And the axis here is x of t is a function of t. So you may say that this signal is linear from 0 to 1. So it's a piece of linear signal. Similarly, we may have other variants of this signal, other combinations of this linear functions. So the functions that are linear in fragments are called as piecewise linear functions. Now my claim is that we can represent any piecewise linear function with the help of unit step signal. Now say for example, let's consider this first example. If we need to represent this pulse that we have drawn here with the help of signal u of t, we can easily see that we can represent this signal as say we are using u of t, so let's consider u of t that is 0 for less than 0 and it is 1 for greater than 0. And if we have another signal, say same u of t but a shifted version of it, so let's say something like this. So we have the same unit step but a shifted one. This being at 1, 0, 1 here, and of course the axis is t here. So you may see that this signal that was given, that is x of t, is actually the result of subtraction of these two signals. So we can see here that this signal that is u of t here and this signal that is u of t minus 1, if we subtract these two signals, you will get the original signal. So we can represent this x of t as u of t minus u of t minus 1. So you may see that here from 0 to 1, this signal is 1. You can see that, and till that point it is 0 for u of t minus 1, and if we simply subtract these two, we'll get the original signal. You can readily see that. Similarly, let's take another example, the second example. Now, what if we need to represent this signal with the help of u of t? How can I do that? Now, if you want to do that, we can observe that firstly the slope of this signal here is t. So the slope here, you can see that the slope here is 1. So the signal here, this signal here can be represented as t, just because the slope here is 1, because y2 minus y1 upon x2 minus x1, that is 1 by 1 times t, will give you the signal that is being represented from 0 to 1. So this signal can be thought of as, our aim is to represent this signal in terms of unit step signal. So how can I do that? Now you can observe here that this signal that is being given can be thought of as a multiplication of, say, if you have the signal t that is everlasting, so let this signal be t, and we can see that we can obtain this signal. It is same, the given signal is same as that of t, but it is being shunted, it is being stopped at t equals to 1. So we may make use of this, what is called as a box function or a window function, in order to obtain this given signal. How can I do that? So if I simply take this function here and multiply this function with this signal, so I am simply multiplying, let me draw it again. So here, if I'm having the same box function, that is 1 from 0 to 1 and 0 otherwise, and if you multiply these two, so if I multiply these two, we can see that we will obtain this original signal, because this function, the second function that we have drawn here, is 0 and it's only 1. It takes the value of 1 only in the interval of 0 to 1. Therefore, whatever comes in this interval will get multiplied by 1. So this part will retain and the other part will be multiplied by 0. So how can we represent that? It is simply as t being multiplied. T is nothing but this, the first representation, t being multiplied by the box function here that we already know, that is u of t minus u of t minus 1. What is this? This is the signal x of t. Now we can see that such kind of signals which are piecewise linear can be represented using unit step signal. Let's see another example. Say the signal is something like this. Let this be x of t, the amplitude being 1. Let this be 1, 2 and 3 there. And let this slope here, we can see that this slope here is 1. Now how can I represent this signal? You can see that this signal, as we have learned, that this is a piecewise linear signal. It is linear in pieces. So let's go for the representation of this signal step by step. So first let's concentrate on this one. Now we have already seen how to obtain this signal from here to here. We can represent that, as we have learned from the previous example, we can represent that as t times u of t minus u of t minus 1. Now what about this? This signal also we have already seen, that is a box function, but now instead of being there from 0 to 1, it is there from 1 to 2. So this we can represent it as the second function. So let me label those parts. So let's say this is part A, let this be part B, let this be part C. So this is part A representation. Part B representation is u of t minus 1 minus u of t minus 2. And part C, similarly part C, we can observe the part C. What is the slope here? The slope of this part C. You can see that y2 minus y1 upon x2 minus x1, that is minus 1. So y2 minus y1, that is the signal here, is y2 minus y1 upon x2 minus x1, that is the slope of this, multiplied by t, so that is minus t. And this signal here, this signal is being shifted by the amount of 3 units. So we can see that this signal, only the one which I am emphasizing here, this signal. So the part C signal can be represented as, you can see that this signal is being obtained by shifting the signal t or minus t to be specific. So we want the signal to be this one. We want this signal. Now this signal can be thought of as the multiplication of the box function that we have seen and the slope function, that is nothing but minus t, and that slope function being shifted by an amount of 3 units. So how do we obtain this signal? Now let's obtain this signal step by step. Say we have this signal t. Now in order to obtain this signal, we need to flip this signal and then shift it by amount of 3 units. So if this is t, if we simply flip this signal and shift it towards right by 3 units, the resultant signal would be so I'm flipping and shifting this signal. So the resultant signal would be exactly what we need. So I'm shifted the signal by 3 units towards right after flipping. So what is this signal mathematically being represented as? So this signal can be represented as T being flipped and then being shifted by 3 units. So this is the signal, but this signal is everlasting. So if we want to restrict this signal, what I mean to say here is we want the signal only to be present only during 2 to 3. So we'll have to stop this signal, we'll have to shunt this signal using the box function that we have already seen. So this function, if we simply take this function and place it here, it will simply take out the part of this signal from this position. Otherwise, this signal T would last long from minus infinite to infinite. So this is the T function actually. In order to obtain only the desired position or desired portion of the signal, that is, we want this signal to be there, this signal can be represented as minus of T minus 3. So the equation turns out to be minus T plus 3 whole being multiplied by U of T minus 2 minus U of T minus 3. Now what is this? This is the signal, this one, minus T plus 3. And what is this? This is the box function which we are using in order to just take out the portion that is desired in the signal. So we want only this portion from 2 to 3. So we simply multiply the original signal that lasts long, so that is minus T plus 3, with the box function. So that will simply take out the part that is desired. So the original signal here, that is x of t, therefore can be represented as a plus b plus c. All three equations will be added, so it turns out to be the addition of all three equations. So I simply need to add all of these three equations. Now I'll give you some problem for practice, so just try it out. Example: say you have signals something like this. Let this be minus 1, let this be plus 1, x of t, the function of t. Some more. Let these positions be 0, 1, 2 and 3. Let the height be 1, x of t. Here let it be minus 1. Now the task is try to represent these signals using the unit step signals as we have done in the previous two examples. Try to do that.